Hello guys. Uh, this tutorial will go over, in this tutorial we will go over trigonometric limits. But first, before we go over trigonometric limits, which could get a little bit tricky, we need to first revise what you know about limits. Okay. To find the limit of a function fx, okay, I'm just going to revise quickly, so I'm not really gonna go deep. Okay. So if you're trying to find the limit, okay, limit of a function, let's call it fx, okay, as x approaches a constant, let's call it a, okay, so a is a constant, okay, so the limit of this is going to be exactly fa. Of course, this is not necessarily true, okay. Why is this not necessarily true? Is because if I have a function, okay, let's say that this is my function, okay, and it's kind of very weird. Why? Well, because it kind of looks a little bit like, let me draw in a different color. It kind of looks a little bit like this, okay? So it's going all the way normally, okay? But at the point A, right here, this is x equal A, okay? At A, it's undefined. Okay, what do you mean undefined? When there is a function that is undefined, we kind of draw a circle that is like this, okay? So we do not know the value of y, okay? So at this point, we don't know y. I mean, we if well, we it's not that we don't know why, but if you actually substitute n the values, you wouldn't get a value. If you try to find the y from your function, you wouldn't get n your y. Okay, so this is our problem. Okay, and this could happen. If this is the case, then doing fa, substituting each x with a, would actually not be very helpful. You could get something like, let's say, you could get something like 0 over 0, or perhaps infinity over infinity, okay? This infinity over infinity or 0 over 0 doesn't really make much sense, and we call this a non-defined value, okay? So, so in this case, my limit is not really going to be fa, it's not the direct substitution, but something else. So, yeah, we're just going to get something else, okay? Now, I'm not going to go deeper. Alright, so let's continue our revision with the second idea, is that if we have a multiplication of two functions, and let's call them fx and gx, okay, and we're trying to find the limit as x approaches a, so let's write this down. The limit of x as it approaches a, I mean as x approaches a, for fx multiplied by gx, so any two functions multiplied together, okay. This this could also exactly mean the following. Okay, what do you mean? Well, it could also mean this. Okay, you can take the limit as x approaches a for fx, okay, multiplied by the result for this multiplied by the limit of x that approaches a for gx. Okay, so I hope you can see why. Okay, so now let's say that my fx, okay, this is the third part of our revision. Let's say that my fx is actually equal to 3. So it's a constant. If we try to draw it, okay, if we try to draw it, let me change the color. Okay, so if we try to draw it, it's something, I mean, it is actually looking exactly like this, okay, where y here is equal to 3. So if you take the limit for this function, so if you take the limit of x as it approaches a, whatever constant is, okay, and let's put this a here, so this is a, okay, for fx, or let's not say fx, let's say 3, okay, what would this be equal? Okay, this is the question, what would this be equal? But this is kind of a very stupid idea that you know, it's not something that is weird. I mean, if you have a function that doesn't change itself over x. I mean, y itself is always equal to 3, right? So if you try to say what is y at x equal a, it's going to be 3. At x equal 4, it's going to be 3. So the function is always equal to 3. So if I ask you what is the function approaching as we approach any kind of x, okay, the value will tell me is 3. Okay, so the result for this is actually 3. All right. Okay, this is the last idea, and we will actually use the last two concepts. Okay. Now let's say that we are trying to find the limit, okay, of x as it approaches a, okay. I mean, as x approaches a for a function for 3f(x), okay. And this idea actually uses the last two ideas, okay. So if I call my 3, okay, if I call it gx, or if I think of it as gx and uses the second idea, okay, what I would what can I how I can put it is that, okay, the limit as x approaches a for 3, okay, multiplied by the limit of x as it approaches a for fx, right? I can do that. And from the last ideas that we have discussed, I'm really sorry, the brackets look messed up. Um, from the last ideas that we have discussed, we can see that this is actually equal to 3, right? So this is simply 3 limit x as it approaches a fx, right? This is exactly the same. So these two, okay, let me show you in a different color. These two, this one and this one, are equal, right? So what can this mean for us? Okay, what does this mean is that these three, if you have a constant, okay, if this constant, you see this constant, you can just take it outside, okay, you can just take it outside. So any constant you have, okay, you can just take it outside, okay. Okay, so yeah, this does make sense. Okay, I didn't even need to show you this. Okay, but just to avoid confusion later. Right, and now that we're finally done with our revision, we can actually begin our trigonometric limits. And the very first limit we will look at is a very famous one. Limit of theta as it approaches 0. For sine theta, sine theta over theta. Well, this looks very weird. So sine theta over theta. Okay, if I directly go ahead and try to substitute in values in here, okay, like we have said in the revision, the sine 0 is going to be 0, and theta is going to be 0. So we have a 0 over 0. Now, is this value equal to 0? No. Is this value equal to infinity? No, we don't know. This is an undefined value. 0 over 0 is an undefined value. So what do we do? I mean, this is kind of annoying. What do we do now? Well, the first thing we can think about is actually drawing the graph of this function. Okay, so let's go ahead and draw it. Let's draw the graph. Okay, and on the y-axis I'm going to put my sine theta. On the x-axis I'm going to put my sine theta. So this is theta. Okay, and this is sine theta. Okay, theta and this is sine theta. And of course, this is a very, very famous graph. It looks something like this, right? And if we actually, I'm just going to draw it more accurately. And this is just to make it clearer. I mean, it's important to look correctly in this example, okay, or in this. So it's more like this, okay. Now, so So it looks like this. This is my, this is my graph. So what are we trying to do now is, okay, we are trying to find the limit. Okay, we're trying to find the limit of sine theta over theta as my theta. Okay, so as my theta approaches 0. So we are going this way. Okay, and we are trying to find it exactly right here. We're trying to find the limit exactly right here. So what we'll do is what we'll do is actually look at values that are very close to theta but aren't exactly theta. So let's look at, okay, let's look at O at when theta is equal to, let's see, when theta is equal to 0.5. Okay, it's a value that is very close, but it's not exactly close. I mean, it's not exactly 0. So sine 0.5 is going to be equal to, I mean, I'm just going to use my calculator. It's going to be 0.479, okay? 0.479, okay? So here sine, this, if we try to actually evaluate our limits, okay? But as x as theta approaches 0.5, or if we can just substitute in 0.5 in our function. So we are going to divide this value, okay, this value by this value, right? Because sine theta is over theta. So the result of this is going to be, okay, the result of this is going to be, okay, it's going to be what? It's going to be 0.9585. Okay. Okay, we are happy with this. Now let's try it let's evaluate our function again, the same way we did it here, but at theta equal to 0.1. Okay, we want to get closer to 0. So at theta is equal to 0.1, and notice what we are doing here. My sine 0.1, okay, is going to be equal to what? It's going to be equal to 0.0. Okay, so it's equal to 0.09983. So this is going to give me a value that is, I mean, when we divide sine 0.1 over 0.1, sine 0.1 over 0.1, it's going to be equal to 0.99833. So as you can see, we are actually getting close to the value of 1. Okay, let's try a very closer value to 0. Okay, let's try at theta is equal to 0.01. So my sine 0.01 is actually, this looks weird, is actually equal to, let's try sine 0.01. It's going to be, this is a very ugly value, 0.00999, okay, 983. And this is when we divide sine 0.01 over 0.01, okay? So we divide this by 0.01, we get a value that is equal to 0.99949, yeah, 83. So this is a very, so as you can see, as we get closer, okay, let me try a different color here. As we get closer, I mean, we were 0.5, and as we get closer to 0, okay, you can see here that this value of my function gets closer to 1. So the answer for my limit, okay, the answer for this limit is actually 1. Okay, and good job, guys, we have done it.